Hello, class. We're going to look at our chapter 6, which is columns now. So the first thing we want to talk about is why do we care about columns when we're talking about machine design? Well, the thing with columns is it's not just about columns; it's about any sort of shape that is long and slender and has the capability or the possibility of buckling. So if we take a shape that has something like this, and we apply a load so that our part or our element is in compression, and the load, and we'll use the letter P to stay consistent with the book for this particular chapter. The load exceeds a certain critical loading factor, or not loading factor, critical load, we will have buckling in our part, which is to say that if you have a piston or a shaft or some sort of similar machine element that you're designing and you have too large of a load on it, you're going to buckle your part, right? So that's why we care. So moving forward, let's get this pen working. As you may have discovered in the last couple lectures, my screen is cracked, and my pen and my screen tend to do whatever they want from time to time, but we'll just force them back into cooperation. So the first thing we're going to look at is the properties of a cross-section of a column. So if we look at, there it goes, we do something like this, and then we do something like this. All right, so the first thing we're going to look at is section 6-2, which is the properties of the cross-section of the column. So what's important when we look at a column or a member that we're going to evaluate for buckling? And first thing we want to look at is the area, right? So we have some sort of member. Let's draw something like this, right? So we have the A for area, cross-sectional area, right? The other important factors are the area moment of inertia, which is denoted by the letter I, moment of inertia, and the lowercase r, which I draw like that. So hopefully you can make that out with my chicken scratch. Is the radius of gyration. Right? So when we look at the area, we're looking at this face, right? Right here. We look at the area moment of inertia and the radius of gyration of that particular face of the member, because we'll load it in a direction, if I can get the pen to work, like so and like so. All right, where we'll use the letter P to denote our load. All right, so if we combine these three terms and we want to relate them all to each other, we can say that the radius of gyration is equal to the area moment of inertia divided by the cross-sectional area, quantity square root. And that's equation 6-1 in your textbook. And if you recall from mechanics of materials, there's a derivation for how to find that. We're not going to delve too deep into that or into it at all in this course. We're just going to accept that we know that's a fact, and we're going to move on. So what we want to do is look for our minimum area moment of inertia, I, and our minimum radius of gyration, R. And we'll take those into account here in a little bit. So the next sort of important concept we want to look at as we continue our discussion on columns is section, frustrating, section 6-3, which is end fixity, or fixity and effective length. I'm not sure I'm pronouncing that correctly, but that's okay. Write it out in theory. End fixity, F-I-X-I-T-Y, and effective length. All right, so The idea or the concept behind this is that if we have a column, right, and it's something like this, and its length L here, depending on the different conditions, and I'll change colors, depending on the different conditions at the ends, we can have different effective lengths, which will be we will be able to calculate based on theoretical and practical values that have been established. So moving back to our black color, if we consider some cases such as a column that is pinned at both ends, like so, we can say that the column is free to rotate about these pinned ends, but it's not free to translate, right? So it can rotate, and if you have a buckled column, you might have something that has the shape like that. Right? Maybe I'll draw that a little better. Like that, right? So this is our buckled column right there. Buckled. All right. So these ends here and here have rotated, but they haven't translated. And if we denote the length of this column, the original length, come on now, of the column to be L, as we previously stated, the theoretical and practical effective lengths can be calculated based on our constants. So what we have is our effective length, which we'll denote by LE, length effective, is equal to K, which is a constant, times our original length. And this is equation 6-2 in your text. All right. So the L is the original length of the column. K is our constant, which is going to be based on our end fixity, right? Our conditions fixed at either end, here and here. All right. So this is called a pinned end. Pinned end. So we call this a pinned condition. And this is our base condition, right? So our K, our theoretical and our practical K values are set to 1.0. And this is based on, I wouldn't say experimental data, but I would say practical real life examples of our columns, all right? So moving on, or not moving on, but let's consider some other conditions, right? So let's look at perhaps a column. Let's do it right. Where it's fixed at both ends. So it's not free to rotate and it's not free to translate at either end. So this is a fixed condition. Right? So if I draw a buckled column in this particular instance, it would look something, let's do that better. Look something like this, where our effective length becomes 0.5 of our original length, right? Where this is our original length L here, right? So this is a fixed condition. So what we say is that our K value in this case is equal to 0.5 for theoretical. Now in practical or realistic, we can say that our K value is approximately 0.65. All right. So this would be something like a column supported by 2 floors in a building, or perhaps a shaft in some very tight, rigid journal bear, or not journal bearings, because those allow rotation, but some very tight fitting sleeves or bearings like that. All right. Okay. So that's another example. Let's move on and consider a third example. Let's draw a base here, and we'll call this column. Ooh, that was terrible. Let's try that again. Like so. And we'll say that this is the original length L here, where we have a fixed end, fixed, and then we have a free end, which is free to rotate and translate. All right, so if I were to draw in red something that looked like this, that would be our buckled column right there. Now, if I were to extend that down a little bit, like this, what we could say is that our overall length here is now 2.0 L here, right? Where the original length was just L. So this is a fixed free condition. So we will change our color back to black. And we'll say that our theoretical K value is equal to 2.0, and our practical is equal to, our K is equal to 2.10. All right, notice that these practical values for our fixed and our fixed free end are higher than our theoretical as we look at these, which generally denotes that we're being more conservative and more safe because we're increasing the effective length of our column and considering a worse case scenario, right? And the final condition we're going to look at in columns right now is a fixed pinned condition, right? So if we have a column that is pinned at the top and fixed at the bottom, if I can draw it decently, right? We're fixed down here, so it's free to, or it's not free to rotate or translate, and we're pinned at the top, so we're free to rotate but not free to translate. We would have a buckled column that would look something like, not like that, like that, where we could say that the effective length is 0.7 of our original length, right? Which I will draw in black here as L, like so. All right, so our theoretical K is equal to 0.7, and our practical, again being more conservative, is 0.8 K, right? So looking through all of these situations, remember our base is a pinned pin where we say K in practical and theoretical is 1.0, and we have equation 6-2 here, which I'll rewrite down here. Equation 6-2 in our text, our effective length is equal to our constant times our original length. All right. So these are some cases that we'll consider and looking at our effective length. So now what do we do with our effective length? Well, we're going to take that into our next section. Assuming my pen will start working again. Our next section, 6-4, which is our slenderness ratio. All right, so our slenderness ratio is simply the relationship between our effective length of our column and our radius of gyration. So we're relating, so let's say we have a square column, like so. We're relating the cross-sectional area and the area moment of inertia to the effective length of our column. And we do that by the slenderness ratio, which is capital S lowercase r is equal to effective length over our radius of gyration at its minimum, right? Or we can also say that's equivalent to our constant k times our actual length, L, divided by our radius of gyration at its minimum. That's equation 6-3 in your textbook. All right. So we will use the slenderness ratio as a guide and a helpful tool when we evaluate our design conditions. All right. So taking these forward, we're going to go to 6-5, which is our long column analysis. And we'll get into what the difference between long columns and short columns are, likely in our next video. But for now, we're going to assume that we're using a long column. And if we go back to Mechanics of Materials and we look through that textbook, I'm sure we can all find our derivation for the critical load. And so I will write it out here, and we'll accept it as a given for the purposes of this course. If you have more desire to know more, we'll look at it together in class. So equation 6-4 says that our critical load, P critical, is equal to pi squared times our modulus elasticity times our area moment of inertia divided by our effective length squared. Right? This is equation 6-4 in our text. Again, this is derived in other references in previous courses, so we can kind of take it as a fact. Right? So notice that in this equation, on the right-hand side, we are not considering the strength of the material. It's all based on the geometry of the material and the modulus of elasticity. Right? So it's all material properties and geometrical properties of our design. So the objective of a design problem is to specify the size and shape of a column that can carry a certain load. Right? So if we recall from equation 6-1 that, oops, that's not helpful, that 6-1, that our radius of gyration is equal to our area moment of inertia over our area square root. We can rewrite this formula and say that our area moment of inertia is equal to our radius of gyration squared times our cross-sectional area. And then if we plug this, so I'll write this geometry plus mech prop for mechanical properties. If we plug this in up here, we can rewrite our equation as P critical, our critical load, is equal to pi squared modulus of elasticity E times our area times our radius of gyration squared divided by our equivalent length squared, like so. So if I rewrite this even further and I take this r squared and I drop it all the way down to the bottom, I can say pi squared modulus elasticity E over area over effective length over radius of gyration quantity squared. Notice that from equation 6-3 right here, our effective length over our minimum radius of gyration is called our slenderness ratio. So we can rewrite this to say that our critical load is equal to pi squared modulus elasticity cross-sectional area over our slenderness ratio, SR squared. And that's equation 6-6 in our text here. So great, grand, good, all well and good. What do we do with this? All right, what use is this for us? Well, if we say that we want to design a column, right? We want to say that we have a column here, so I'll just draw a line here, kind of denote that, we have a column and it's got a load on it, and we say P for load, right? And it's got a certain cross-sectional area and an area moment of inertia and a length and a K value, a constant for our and fixity conditions based on whatever those are. So these are all known. Well, now we want to design or we want to find out how well our load will stand up to our critical load, right? So we're going to take our, oh my goodness, that's not helpful, our critical load, and we want to compare it. Is it less than or equal to our design load, right? Well, if it's less than our design load, then we're not in good shape, because we want it to be the other way. We want our design load to be less than or equal to our critical load. All right, so we take these all, and so we'll say, put this in red, say not safe, and we'll go back and put this in maybe green and say safe. All right, so let's go back to black. So some terms that we want to consider are critical load, or critical buckling load, PA for allowable load, and we'll just use a generic P for our actual or applied load, and we'll use N, as we looked at in section 5-9, as our design factor. There, right? So what we can say is that our, come on, all right, there we go, that our allowable load is related to our critical buckling load by our design factor. So we can say our allowable load is equal to our critical buckling load divided by N, our design factor or safety factor. So what you will end up wanting is a actual applied load, which is less than or equal to our allowable load, which should be less than our critical buckling load, like so. All right. Now, for typical machine design applications, a design factor of 3 is used, and is equal to 3 for, I'll say, typical machine design. And N is equal to 2 for stationary columns. Now, these are general guidelines. There may be codes or regulations or typical standard operating procedures for a specific firm or whoever you work for or whoever you design for. They may have different regulations or guidelines for you to use. Sometimes in construction, they will use N is equal to 1.92. Right? Again, these N is equal to a design factor, or just kidding, there it goes, or a safety factor, depending on who you ask. All right, so what we're going to do is we're going to take a brief break, and then we'll pick this up with section 6-6, and we'll look at the rest of chapter 6 in the next video.